Uh, I think many students are in this same boat. So yeah, walking through those instructions, right? So the very first thing it's doing is saving RBP onto the stack, whatever the base pointer is. So you have to assume, right? We just got here. We don't know how we got here exactly. First thing we do, save whoever called us base pointer. The next thing we do is move the stack pointer into the base pointer, right? So move RSP into RBP means that the stack pointer is, or the base pointer is now at the same place as the stack. And again, we don't know what it is. So you can just assume it's 0 or 100 or 1,000, however you want to think about it, right?
Yeah.
Then what's the next line do that we just talked about?
So, and that's making room for 4.
For how many bytes?
Or 64, but
Yes, 40 hex,
okay.
right?
Yeah,
So
yeah.
it subtracts 40 from the stack pointer. So now it's making room for 40 bytes,
64.
or for, sorry,
Yeah,
40 hex, but 64 bytes on the stack, exactly.
Yeah. Okay, and then, so this like just directly moves this like hex number into that
Yep.
like register, right?
Yep. All right.
Like,
So there's you can think of it as there's the A register, B register, C register, D register, and a couple others, right? And so the way to think about it is this architecture has evolved over time. So it was originally, I think, 8-bit or 16-bit registers, and that was like the A style. And then when they extended it to 32-bit, then they became EAX. So if you see any EAX, like line, you see plus 100 there, the move EAX.
yeah. Okay.
It's a little bit lower. It's like 4 down. Anyways, EAX refers to the 32 bits of the RAX register. Yeah, there you go. And then RAX refers to all 64 bits of the same register. So they're all different ways of talking about the same thing. So cool. So then with that, we can keep going. So yeah, that's a move that whole hex value into the RAX register so that after this instruction executes, absolutely the value inside RAX is exactly that value.
Okay. In hex.
Yes.
Okay. And so then the Q word, that's like looked up, it's like, it says quad words, like
Wait, let's go to the next one right after it. I like doing it step by step,
so
right? Yeah.
the D one.
RDX,
So
yeah.
does it do the same thing just with like that hex value?
Yep. So now it's moving a different hex value into there. I think we're on plus 32. I think it's 3 lines up where we are, or 4 lines up.
Oh yeah, sorry, totally looking at
Yeah.
the wrong one.
No worries.
Yeah,
I mean,
okay.
you can tell it's the same pattern, right? So once we kind of get these lines, we'll get the next ones, and then they just build on each other.
Yep. Okay, so then it moves that one into that one too.
Perfect.
And then this one, so is it like making room or like putting in those like different like hex values into different spots?
First thing we have to ask ourselves, what's the source and what's the destination in this instruction?
Wherever that base pointer, this thing is the destination, right?
Yes. And then what does the brackets mean around there?
Does it just like does it before like that creates it?
Not exactly. It's like the brackets basically indicate, like in C, a pointer dereference. So what this instruction is doing, right? So you already said it, the source is RAX. So, and it's a move instruction, right? That's obviously the very important thing we didn't mention. It's a move instruction, and it's saying move whatever's inside RAX. And the question you have to ask yourself, do we know exactly what's in RAX at this point? Yes.
Yes.
Exactly,
Yeah.
because we have that from 2 lines above, right?
Yeah.
And then where are we moving it? So a move instruction could be like, if you look down at plus 80, you can see that move RDI, comma RAX.
Yeah.
That's a move instruction that says move whatever's inside RAX into the register RDX. So it's just a move instruction between 2 registers in the CPU. So that's different, obviously, and it looks very different than the other thing, right? And the key difference is, so A, the quad word, the keyword tells us that it's 64 bytes.
Yeah.
So it's saying take 64 bytes from RIX, and the question is, where am I moving them to? So I'm moving them into memory, not into a register. And that's what the brackets tell you. The brackets tell you
Oh, okay.
dereference. And so what it does is says, okay, first calculate whatever's inside the brackets, right? So what's that value in the brackets? Take our RBP, the base pointer, which we actually know because of, we don't know the exact value of RBP, but we know from line +8 that it is pointing to 64 bytes above the stack pointer. So it says take RBP, subtract 40 bytes from it, and then copy the 64 bits into that location, and it's going to copy basically up.
Okay, so does that put it like does it begin now where the stack pointer is? Like, does it?
So it happens, it doesn't necessarily, but it does here because we know RBP minus, so actually the thing that I always do when I do this is draw diagrams. Is there any way I could draw on your screen? I actually don't, because I don't know Zoom that well.
I think you can. I think if you grab remote control, maybe.
Oh, how about this? I'll share a whiteboard. Can you all see this whiteboard? Can you see both?
I can't. So I don't know.
No, you can't see it? Okay, they can't see it.
Are you able to annotate on the screen by going to view options?
I can try. It says request. It's like request remote control, maybe. It feels.
Oh yeah.
Okay. Oh wow, this is weird. Okay, but I don't actually want to do this. I want to annotate because this is terrible. Okay, but at least I can. Okay. Wow, this is actually really fancy and scary all in one. Okay, I'm gonna stop doing this because this scares me a little bit. No, I just don't want to have that much power over a student's screen ever. Okay, let me see if there's. People used to always do this, right? Okay, let me do a brief.
I can, but I don't know.
It may not be enabled. I think that's probably it. It's probably disabled by default in this Zoom meeting because of ASU's security things. Is probably my guess. I'm sure you all recall the fun Zoom bombings and stuff. Okay, so what we should do is, okay, let me go run and grab my iPad. Can you copy and paste that snippet into the chat so I can take it and I'll start sharing from my side and I'll start drawing and stuff?
Like from in here?
Yeah. At least the first, I don't know, like 8 or 10 instructions, like not everything, but some of it.
Oh, thank you, whoever did that. Johnny?
Oh, cool. All right, thanks. All right, so I will. And okay. Sorry, I wasn't prepared for sharing my own screen. All right, here we go, share screen. Yay, oh my gosh, that actually worked. Okay, Everyone can see this?
Yep.
Yes.
Okay. Ava, I'm going to be drawing through you. So, okay. So we can ignore this NBR64. It's like a weird, if you Google this, you can find out it's a weird thing, but it's basically a no op, right? So that basically doesn't do anything. We talked about push RBP. And what we can do is I'm going to draw the stack layout as we see it. So, and we don't know the exact addresses, right? But we can just use 0 as our thing. So we can, when we start this program, we can say, okay, right at 0. And the way to remember that all these things work is I'm drawing this pointer that RSP is pointing to 0 when we first call this function. But honestly, I don't actually know that. And I don't even care because what matters is whatever's inside the register RSP, that is where the stack pointer points to. So, okay, so then we look at this first line, push RBP. So whatever was RBP is going to be on the stack. And now, and how big is a register? How many bytes? Say it louder.
4.
Not quite. That's 32 bits.
It's 16. 8.
8. Yes.
8. There we go.
Yeah. So remember, 32-bit means 4-byte register size, and 64-bit means 8-byte register sizes. So in our example, we know that when we push something onto the stack, we know the stack pointer is now actually going to be pointing to 8, and that's RSP. So it's going to be moved down 8 bytes to make room for what we just pushed onto the stack. So we just did this push RBP. And now our instruction pointer is here. And it says, okay, the next thing I'm going to do is move the stack pointer into the base pointer. So I'll draw another arrow here to say, okay, our BP is here. So RBP currently has the value 8 in it. And I just executed that. That's great. I go to the next one. I say, okay, subtract hex 40 from RSP. So now RSP is going to be, oh, it already moved away from here. It's now going to move here. Oh, and here you can see I immediately got a problem because I started at 0, right? Which is probably a good idea not to start at 0. But like I said, we could start basically anywhere. Let's say 1,000. So this is, what's 1,000 minus 8? This is the problem I need to this weird math I don't normally do. Where's my calculator? 992, thank you. And then what's 992 minus 64?
$928.
928, thank you. And again, the difference is the one that matters. It doesn't really matter what it is, but it can help us kind of think about it. Yeah, thank you. Okay, cool. So we did this instruction, and this is honestly, this is exactly a good practice for these assignments are to do exactly what we're doing now and just step through it line by line. And because it's just registers, values moving around. It's of course understanding the semantics here. Okay, so we talked about this. So this is going to move this value into the RAX register. I could put RAX here, and I have that value. I don't know what it is right now. I'm not going to just write it there. But that's what that line does. We know. We go here, and that's moved that value RX414E into RDX. So RDX is going to be 0x43. Sorry, it's at 41. And then we get to here. So now we get to where we're going. Okay, so we're back. Ava, what are we doing now? So what are the semantics of this instruction?
So I think you had mentioned, so it's filling from those 64 bits back and up with the value in RAX.
Exactly. So it's at RBP. Oh, I'm getting some feedback. Okay, there we go. Thanks. Okay, so it's starting at RBP minus, And this is what we can see here. It's at RBP minus hex 40. We actually already know that RBP is at 992 minus 40 is 928. So we're starting here and we're writing onto the stack the hex values of, and we know we're writing 8 bytes total. So to be honest, I'd have to like debug this to remember exactly the order. It should be moving that onto the stack. It should be, so it's 54. So we can just kind of put here OX 54, blah, 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 blah from here, right? So we can make a note to ourselves that that comes from there. And so we know, so how many bytes did we copy?
64. Or 8.
64 bits. 64 bytes is a lot.
So
Right, we
only
copied at the address starting down 64, but we moved whatever's in EAX. EAX is 8 bytes. So we've now copied 8 bytes onto the stack. So this is at, oh gosh, what is it, 936? Is that right?
Yeah.
928 plus 8. I actually really hate doing math like this, so. Okay. Cool, and then now what's the next line?
So it does the same thing.
And what is it moving where? So the thing, yeah, the question you always got to ask yourself is, okay, what's happening here? What are the semantics of this line? So we
now
are
the
here.
RDX is moving to the base pointer minus the 38.
Exactly. And is that going to be 2 bytes above this one? What's the difference between these two?
Is it 16? Like, is
It's
it 8?
probably 8, but I actually don't know. So can somebody translate these? The important point is that to remember that it's hex, right? And that it's not just 2 bytes. So we would calculate what is RBP minus hex 38. We would find out that it should be 936. So we know this is, oops, RBP minus OX38, right? And what am I going to put there? I'm going to put this value, whatever's here, right? So this is OX41 for E dot, 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 dot. And then how many bytes here get copied?
Another 8.
Another 8, exactly. So this is, we know at, what's that? Got another
942.
942. I'm going to take your word for it.
44. I lied.
All right, it's okay. We'll forgive you. All right, at 944 is nothing, right? So we filled in now 16 bytes from the stack pointer minus 40, or from the base pointer minus 40. And then, so now we've done this line. Now we go here. So what's here?
So it's just like overwriting or like reassigning what value is in RIX to that new one.
Exactly. So it's moving a new value into RAX, which is going to exactly replace everything that's in here, what's in here. So that starts with 49. 0x49 dot, dot, dot.
And then it'll do the same thing with the RDX.
And what's the one difference between those two lines besides the register?
Size.
Yes, the size of what we're copying in. So this means that, remember, what this will mean is the most significant byte is 0. Right, because it's like the difference between 10,000 versus 100, right? It's like 0x1000 versus 0x, and this is hex, but whatever, the point still stands, right? The difference between there is there's zeros at the start of this number, and if we think about this number, because we know these are 8 bytes, right? This only has 7 bytes, so the last 7 bytes will be written there.
So would it really be like 005?
Mm-hmm. Yeah, so like if you did move, so if you did RAX 0x 40, let's say, right? What this says is the actual bytes you want in RAX is 40, hex 40, which means the least significant byte is hex 40 and all the rest are all zeros, right? That makes sense because that's what you want here.
Mhm.
So exactly the same thing is happening here. So after this instruction, so we go to execute this instruction, 5954. So here in RDX, I'm going to put 005954. Sorry. Yeah. So the important thing is the 00 at the start there.
Mhm.
All right. Cool. And then what's the next line?
So now again, it's moving the RAX value into
Where?
30 down from the base pointer.
Perfect. Yes. RBP minus 30, which we actually know is 8 different than here. So that should be right here. So this will have 0x 49 ... And right here will be this plus 8, which is what, 952. It's super weird for me that I didn't do this in hex on the side, but it's kind of a little slightly easier. But anyway, okay. Then we can go here. We move here our dx where?
Another like 8 up, so basically on top of the.
Yep. So it'll be right at 952 exactly. We'll copy this value onto there. It'll be 0x005954 ... And then this is 8 bytes ahead. So this lies at 960. And then what about this next line?
So does it just put like a bunch of zeros in a place? Like,
Yeah, exactly. So 8 zeros, right? So fill this whole thing up at RBP minus 20 with a bunch of zeros. So 0x000000, wiping out whatever was there. And 8 bytes of that is 968. There's a question, chat. Does that mean the first 2 insertions overlap? Which 2 insertions?
The one that enters into minus hex 40 and then minus hex 38, since they're not.
These are
8
8
bytes
bytes apart. They are because it's hex. That's the important thing to remember.
Oh, so the other ones are even farther apart then, because it goes 8 hex values.
No. So it's
Oh, I'm
let
sorry.
me-
I'm sorry. Okay, yeah, I was looking at it incorrectly. Yeah.
Yeah,
I
no
get you.
worries. It's the trick. That's why you can't do, like, I can't do addition and subtraction just on hex values because you'll get messed up with like the, the E's and F's. Because that's the crazy thing. You don't see any of the, the A, B, C, D, E, and F values, right?
Oh,
So if
yeah,
you
that's
just try to
right.
do base 10, math on it, you will get messed up. So
Yeah, that
I
definitely messed
always
me up.
either take them, translate them to 32-bit, or just use the programmer mode of the calculator to change them and operate on the hex values directly. Cool, look at that. We're making progress. All right, now what about this line?
I didn't look up what that meant yet. I had already gotten so lost before that. So this is as far as I've gotten. So I'm not totally sure. Is it like putting like it back? Like, is it moving?
Yeah, it looks very it looks very similar to a move instruction, right? And if this was a move instruction, so this is what I think of, right? If this was a move instruction, exactly what this would mean is, where is RBP minus 40? So take RBP, subtract hex 40. We actually know that it's the value, this is RBP minus 40, or minus hex 40, I should, which is 928. Take whatever's, and the brackets here on a move mean take that exact value there and copy it into RAX. So after this, RAX would have 54 ... Whatever is in there is copied to here. That's if it's a move. And so the difference is load effective address LEA stands for load effective address, which basically means if we were moving this, what would be the address that we're moving? So in essence, all it's doing is put in RAX, what is RBP minus hex 40? Does that make sense?
Yeah.
So normally brackets mean dereference, like take, either put something in memory or take something from memory. But here we're not doing any dereferencing with the load effective address. It's really just what is RBP minus hex 40 and copy it into RAX. Yeah, so it's the difference of normally these are equivalent to like a dereference operation, whereas in LEA, it's equivalent to like the address of operation, like the ampersand.
So is RAX that value of like 928?
Exactly, yes. So when this instruction executes, the value inside RAX will be 928.
Okay. Makes sense.
And now what's this?
So that's just loading the value in RAX into RDI.
Yeah, exactly. So it's copying it, right? So we'll have to make another register to keep track. RDI now has the value 928. And what about then the next line?
That's a good question. I'm not sure. I was confused about the different functions too.
Yeah, so I think it said it at the, did it say it in this one?
Yeah, it said it at the bottom. I can read it.
That, yeah, it
said
should
that-
say something like, I have one open too. Yeah, so it says the function string length and puts are from the standard glibc library. So what's the output of the assembly? So this is saying that we're going to call the function string length. This is what this is saying. The other complications are basically just artifacts of how in binaries you call functions. But basically at this point, we are at the point where we know we're going to call a function. And so now we need to look at the x86-64 calling convention. Because we need to understand how do we get to, how do we pass values into the function? So you've, I'm sure, used the string length function before, perhaps, in your C code?
Yeah.
Yeah, so what does it do generally? Like, what's the basic purpose?
How many characters?
Say it again?
How many characters, like places?
Exactly, yeah, how many characters in, so let's actually go look at that real quick. I'm gonna pause and I will bring up. Cool, so you can't see my screen, right?
It's just like where you left it on the.
Okay, cool. Okay, I'm just bringing up the documentation that we can look at. All right, and we're back.
Yeah.
Sweet. Okay, so yeah, so now what we're doing is we're calling this string length function. So just like you said, right? So the semantics of string length, and if you didn't know, you would read this. So the string length function calculates the length of the string pointed to by S, excluding the terminating null byte. So it's how many characters until we get to a null byte. It uses, so it's passed in a character pointer, the first and only argument, and it returns a size t. So now the question is, this is what the function call would look like in, and if we look down, we don't have an example, but we understand how to call this in C. The question is, how does this get compiled into the assembly program? And that happens here. So, so inside here, so the important thing is the system 5 AMD 64 ABI. So I posted a link in Discord a while back, but I can make another one. But this is the calling convention of how you call functions in at the binary level. And so You know, we can read the calling convention of the System 5 ABIs, followed on Solaris, Linux, FreeBSD, macOS, and is the de facto standard among Unix and Unix-like operating system. The OpenVMS calling standard on x86-64 is based on the System 5 ABI with some extensions needed for backwards compatibility, blah, blah, blah. Important things for us. The first 6 integer or pointer arguments. So how many arguments do we have?
1. There was only 1 in the.
There's 1, exactly. And what type was it? Was it an integer or a pointer?
Pointer?
Exactly. Yeah, it's a pointer, right? It's a character point. A character star is a pointer. Exactly. Perfect. So the first 6 integers or pointer arguments are passed in the registers RDI, RSI, RDX, RCX, R8, R9, and R10, which is fantastic, right? So and if we go back to our code, what's the value in RDI when we call string length?
Oh, it's the 928.
Which is a pointer to where?
That the spot, yeah, where your thing is.
Exactly. Yeah, where the cursor is, right? So right there it has many different names. We know in our example, it's the memory address 928, but it's pointing to the start of all of those bytes we copied onto the stack, right?
Mm-hmm.
Now, the other thing we need to look at in this calling convention is where do we get the return value? So we set up all of those, blah, 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 while these values are the first floating point arguments. I don't think we'll have floats, so that's not really, you know. And then after that, as in the x86, Microsoft x86 additional arguments are passed on the stack. Integer return values, so this is important. Integer return values up to 64 bits in size are stored in RAX. So this means that after we call this function and it returns, we should be able to get the result of calling that function in the RAX register. So going back. So this function executes. Now the question, now what's the next thing that happens?
It moves down and like puts in the EAX, or moves up, I guess, more, and puts in the EAX value.
Yeah, where does it put the EAX value?
However many C is.
Yeah, I think it's 12, is that right? Yeah, cool. So this is RBP minus 12. So this will actually be somewhere up here. I think it'll be roughly, oops. Can somebody calculate what that value actually is? 988, thank you. So clearly we have a not for scale diagram here. Now the question is, what is in? So remember, this is the other thing I was talking about. So so we can think of our register RAX here. Each of these is 1 byte. So we have 4 bytes. So the whole thing in total is called RAX. This part here, just these 2 bytes, is called EAX. So they're exact same thing. Yeah. So the EAX is the lower 32 bits of RAX. So it's saying, okay, take that and move it to RBP minus 0x. Now the question is, what is the string length of our string?
Yeah.
So I think this is, sorry, what?
I said, yeah, I'm not sure.
Yeah, so I think that's the important thing. So we know, and remember, we have to go back and look at these. So we know that this is 8 bytes. We know that this is 8 bytes. And we know that string length will start at the very first byte here and keep reading until it gets a null byte. So it doesn't, and this is kind of the really cool thing about the computer, doesn't know or care that, hey, this is at this thing and these registers are here. It says, give me a memory address for string length and I'll keep telling you how many bytes I have to go until reaching. So we know actually that this stack, the current stack we have, down is a negative direction and up is a positive direction. So we know we're gonna start at RSP at 928, and we're gonna keep reading byte after byte until we get to that null byte. So it should be, and this is, thank you in chat. So we know how many bytes are here.
40 or 8 in the one.
8, yep, 8 in the first, 8 from the very first RAX. And we can look, are there any null bytes in here? Well, what do I mean by null bytes specifically? Yeah, 0x00. Awesome. So no in there. So we'll keep going and we'll keep going up here. How many bytes here?
So that's another 8.
Should be another 8. And then here,
Another 8.
another 8. And then here,
Another 8.
is it 8?
Yeah.
What was this one? This one was this one.
Oh.
How many non-null bytes are there here? I can't hear you.
7.
Yeah, 7. Thank you. Now, this actually could be a question mark. I'd have to run a quick test because the question is, where is this null byte located? Is it at the most significant bit, the farthest away, or the least significant byte? So remember, if we go back to 230 and you learned about endianness, right? We have to always be thinking about that. So for instance, if I have, oh, this is a wrong diagram because there's not enough places. Oops. I just realized this. This should be bang, 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 bang. Okay, but if we think about 32 bits, because that's easier, if we go 0, 0, 0, 1, 1, 2, 2, 3, 3. So it's a 32-bit number, 4 bytes. Now the question is, how does the computer actually store that? Does it store that as 0x00, 0x11, 0x22, or 0x33? Or is it 0x33, 0x22, 0x11, 0x00? So how do we figure this out?
Google.
Google, yes, definitely Google will help. It is Little Indian, right? So we could look up, yeah, we can look up x86-64 endianness. Can somebody double check? I know Nicholas just put in the chat. I believe it's Little Indian, but then I can't remember which one of these actually is Little Indian. So this is Little Indian, which would mean that, so if this was memory address, this would be at 0, 1, 2, 3. Is that right?
Yeah.
Oh, you said the
see.
first one, sorry, not the second one. So, or,
That's-
see, we're all confused. Okay, the way to settle this is to Okay, let me, good. Okay. It's just a double check. This is what I like to do. Test.s. We could write a quick assembly program to test this. We could say move. What was the? So I had some example, right? So into RAX. Let's say 0x 0011223344 1 2 3 4 5 6 7 8. Right, so we're just putting some value that we can see right here into the thing, into RAX, move into RSP, RAX. Same good-ish. So everyone understand what I'm trying to do here?
Yeah.
Yeah, so move this value into RAX, just move it onto the stack so we can then look at the stack and see what this looks like. Cool. All right, GCC. All right, cool. And I need some way to, can somebody, or I can Google. So the problem is I'm using not standard, so the standard x86, sorry, the standard GCC syntax I believe is AT&T, and this uses Intel syntax. So GCC, I should be able to just, yeah, there we go. There's a command to dash M ASM equals Intel. No, and dash capital S maybe. That doesn't help. Too many memory references for move. Oh, I think I'm missing the keyword stuff. Okay. Was it, and it was pointer like that? I don't usually write, maybe it's, okay. I'm just going to switch the syntax because this is way easier. It's exactly the same stuff that we've been looking at, but just a different syntax. So no instruction manual. Operand type match. Move. Oh, move abs maybe is the problem.
Yeah, that's what it used in the studio one.
Okay. Okay, I'm just Googling how to do that. In some with gas, with move SQ. Okay, cool. So that's Q. I was missing the Q here, and I believe this means a constant value. Why is it still saying operand type Match. Googling is your friend. Oh, because I messed everything up. That's funny. Okay, my syntax was wrong. These should be percent signs. There we go. So registers are percent signs in AT&T syntax, and constants are dollar signs. Defined reference to main. GCC. Okay, I must be missing something. Am I missing .text? Oh, there's a way to export main. Export main. Honestly, I probably could have GCC. There we go. Okay, .global. Cool. So this is saying, hey, this .text means this is code. .global means export main, so that it can be picked up by everything else. There we go. And of course, this actually doesn't do anything, so we'll do it in GDB. Breakpoint on main. Start. And look, there's our instructions. All that work, we did it. We did it, everyone. So move this into RAX, move RAX into RSP, return. Okay, so I'll walk through this and I'll show you P/. There's a couple things you can do. Info registers will tell you the value of all the registers. So you can see RAX has this value. This is exactly what we were doing by hand on the handwritten thing, right? So if I do a step instruction, it will execute, and your GDB will look different when you do this at home. I'm using an extension to GDB called GEF that shows you this debugging output. But the commands I'm typing in are things that you can so X 5i $RIP. This will show you the current instructions where the instruction pointer is pointing. So we know I just did move that custom value we had into RAX. And if I do info registers, that should show me that the value inside RAX is this value. Awesome. I can also do print /x $RAX. So this means print out, and then the /x means hex, the value inside the RAX register. So that's what this is telling me. And if I go back to this is examine /5 as instructions, the RIP instruction pointer. So the next instruction is going to move RAX onto this onto wherever the stack pointer is pointing. I step instructions, and now I run info registers. Oh, info registers isn't going to show it to me, right? Because I moved it where the stack pointer is pointing. So I can do X 30 X $RSP. G is for giant values. Okay, so we can see here RSP has the value inside of it of 7 FFFDE88, and the hex value there is that value we put there. So yes, this actually worked exactly how we thought. That is fantastic. Now to answer the question of what is the actual value there, I have to figure out GDB print variable examine. It's printing out the whole value here, but what I want is so I'm looking for is what that actual value is right there. So GDB. There we go. Bytes slash B. Okay, so this number is increasing. So at 88, it's 0x7. At 89, it's 66. At 88, 89, 88, 89, 80A, sorry, my hex is bad. 80A, 80B, 80C, 80D. So, and what was our original number? Well, we actually have it right here, right? We have 0011. So at that memory location, so it is Little Indian. So going back, who mentioned that?
I think it was Gianni.
Yeah, good job. So we know this will go at the smallest memory location here, right? So it is laid out exactly this way. And this means that for this one specifically, the string length here should be 8, 8, and 8.
Oh, because it would stop at that first.
At that null byte, yeah, which would be on the smallest one, right? So it's the most significant, it's stored at the lowest, and lower values are here. So as it's going up, it will get there. Yeah, exactly. And that'll also help you how to write out and understand exactly how these characters are laid out.
So then in the EAX value, so if the string length is what, 24, then is only half of that in.
So 24 is less than, so 32 bits can hold up to 2 to the 32, which is like 2 billion or something. So yeah, it's just going to be 24. It will move that into RBP minus there. So it should be, which we said was here. And so that should be 24.
Okay.
But you may have to double check this. I'm doing this all off the top of my head. So.
Okay.
And then, yeah, this next one, right, moves 0 into RBP minus 8, which will be here, which we didn't diagram. There'll be a 0 there, and then it will keep going from there.
When it does the Caesar plus whatever, that's like the line number it's talking about, right? Like it jumps ahead to.
Exactly. So it's jumping to this 121B, which would be one of these addresses. And yeah, it'll tell you Caesar plus. So this is this is Caesar plus 0, plus 4, plus 5, plus 8, plus 12.
Mm-hmm. Yeah.
Cool.
Wow. Okay.
Yep. Just got to step through step by step.
Cool. I think then, so I guess like maybe just like some of the other like keywords, like when it says like byte pointer versus the like D word or Q word, like what's the difference between?
Can you show me the example?
Yeah. It's just like later on in the, it's like in the second half, like when it says like, byte pointer, is that super different or is that just like?
So yeah, that means that's what it's saying about the size. It means that it's only moving 1 byte. So rather than the other move we saw with the D word or Q word was moving all 8 bytes. This is only moving 1. And AL is the least significant byte in the A register. So this would move whatever's in AL into RBP minus 1.
So where does the AL come from? It's from the RA.
Exactly. RAX and so AL, RAX, EAX are all the same registers. Let me find something real quick. Oh, this is actually a nice diagram. I don't know if this translates well into the chat, but nope, it does not.
You can stop sharing. You wanna put it up?
I had a really good diagram somewhere. If you make a Piazza post asking about it, I will pull up that diagram and I can share it with you.
My last part is then, so for the output of
Oh,
every,
sorry, just a second. Here, this is actually a decent one here in this. This is the an x86 assembly, x86 architecture. So it's like showing a little bit. It's not as graphical as I would like, but that. Or does
Oh,
it
yeah.
look nice?
yeah.
Yeah, so it shows that like AL is the last byte of the RAX register and AH is the second to last byte of the RAX register.
Yeah, no, yeah, that makes sense.
Cool. Any other small questions? I have to run. I'm late for a meeting, but I was late here, so.
Yeah, I had a small question.
Sure.
So I'm doing the Stack Overflow things, like part one,
Mhm.
and I did everything, and then I go all the way up to the end where I'm like, okay, I'm gonna make my code to make a certain amount of bytes, and then with the win condition at the end, and then yeah. But when I run my program, it doesn't let me create a file. Like it says I permission denied when I try to like create a file and then write my stuff to it. So is there a way to get around that, or like should I put it in a different place? Right now I'm trying to put it in temp.
Yeah, I don't know enough about that specific challenge to tell you exactly. I think, yeah, I would look at the what's the word I'm looking for? Sorry. Yeah, if you have the binary, look at what file it's trying to open and create that file or that directory.
Oh, okay. Thank you.
Yeah, it's probably that it doesn't exist is why it's saying that file not found. The other way you could do this is if you run, so let me show you something real quick. A super nice thing to help with debugging is, and it's a lot of output, so don't be too overwhelmed with what you see, but you'll definitely see it in there, is, did I just share my whole screen? That's not what I wanted. Yeah, there we go. Can you all see my iPad? Oh, there we go. It's popping up. Oh, okay. Can you see this?
Yes.
Okay, cool. So you can, there's a program called strace that will run a program and show you all of the system calls into the operating system that it's making. So for instance, like with this program, so I'm just running ls. And it, of course, is, but it's telling me everything that it's calling. So for your case, it should call an open call at some point. And it, like here, it's telling me exactly what it's outputting. Like it's outputting this test.txt, this, all the things that's outputting. It does the same with file operation. So it would actually tell you what file it's looking for, and then you can create that.
You know what? You're totally right, because I'm looking at my code now, and I thought I was doing something to create a file, but I was doing something to open it. So yeah, it's probably that I had that. Yeah, it doesn't exist, so I have to create it first.
Awesome.
Yeah.
Cool. Okay. Then the other question was, is every homework with the same overall weight? Yes, every homework assignment is weighted the same.
Professor, I had another question about assembly 0. It's the
Mhm.
thing I messaged you about over Discord where I think I'm putting in the correct answer and it's always saying it's incorrect. And I asked the TAs about it and they don't even know why it's saying my ECX is incorrect, but my EAX is always correct.
Okay, make a Piazza post, please, because a private one, and put what you're putting in so that we can double check it on our ends. That
Okay.
that way it'll go to all the TAs, and all the professors.
Private Piazza, you said?
Yeah. Just set your post to private, and we'll find it.
Okay.
Cool. All right. Thanks, everyone. Sorry I was late. We went a little bit over, and I'll share this online. Bye.